welcome you all to Physics Unveil. My name still remains Franklyn Einstein, and today we're talking about the application of Gauss law part 2, right? And now in this application we'll be talking majorly on surface charge density. All right, so in our last video on the application of Gauss law part 1, we talked about how to use the right equation when you see a spherical question or a symmetrical question. Now I want to go over into surface charge density, and let us explain the whole concept now to you. Now, if you remember, electric field obviously is equal to kq for what? R squared, right? Very important. And remember what k is. Remember that k is equal to 1 over 4 pi epsilon naught, which is the permittivity of what? Free space. Now if I put this equation over here, I'm having that E is equals to Q over 4 pi epsilon naught R squared, right? But if I arrange this very well, I'll be having Q over 4 pi R squared epsilon naught. Am I right? And if you check very well, this is like the area of what? Of a sphere, right? So this will give you Q over E naught. But now, this Q over E naught, which is writing Q over A times 1 over epsilon naught. Am I right? We just separated it. And charge over area is something we call surface charge density, or we put sigma for that. So this is equals to sigma times 1 over epsilon naught, right? And that will give us something as this over what? So this is our electric field when we have the surface charge density, right? Electric field is equal to the surface charge density divided by the permittivity of free space. Units for surface charge density: coulombs per meter squared, right? The unit for this is what? Coulomb per meter squared. So this is what you need to know about surface charge density when you're doing electric field. So remember the manipulation. Remember, electric field also is equal to Q R squared, and this is also equal to surface charge density over this, right? So it's just a little bit of mathematical manipulation. So now let's go into a question, and then let's see how we can solve a question. So now let's move into the question 1. So now the first question says a 100 electron is fired directly towards a large metal plate that has a surface charge density of 20 times 10 to the power of 6 coulomb per meter squared. From what distance must the electron be fired if it is to just fall to strike the plate? This is a very simple question. So remember our steps taken. First write the parameters and so on. So solution. What gives us a 100 electron. Now anytime in physics you see electron volts, you're talking majorly about energy. And in electric field here, we're talking basically on electric potential energy. I know we've not touched that, but we'll touch that when we enter into capacitors and capacitances of capacitor, right? But just for a preview, now the potential energy or electric potential energy is equal to charge times the potential itself, right? Charge and what? The potential itself. And now mind you, the potential itself is equals to electric field times distance. Obviously that's correct because electric field is equal to both voltage over distance, which is volts per meter, right? So therefore voltage is equals to electric field times what? Distance. Alright? Good. Now let's also guess what our energy is. 100 electron volt electron. Now mind you, 1 electron volt is equals to 1.6 times 10 to the power of negative 19 joules. 1 electron volt is equals to 1.6 times 10 to the power of negative 19 joules. Please make sure you are jotting. Very important. So now, therefore, 100 electron volts, 100 electron volts will equals to 100 times 1.6 times 10 to the power of negative 19, and this will be 1.6 times 10 to the power of negative what? 17 joules. Now we have our energy, our charge here, obviously, because a particle is being specified, which is electron, therefore the charge will be the what? The electron charge, or the charge of electron, which we all know that is constant, because the charge of electron is equals to 1.6 times 10 to the power of negative 19 joule. Now gets confused. Alright, now you have a charge, right? We ask for what distance, so therefore we're looking for D. D is what we're looking for. So our D is what we are looking for. We're looking for distance. But now what about our electric field? Because obviously we need to find the potential itself. But we don't have electric field, am I right? But we know that electric field is equal to surface charge density of Earth's permittivity of free space. Now, since we know this, we just impute our values. The surface charge density is 20 times 10 to the power of 6 divided by what is the value of permittivity of free space is 8.85 and 10 to the power of negative 12, and therefore E will be equals to 2.26 approximately times 10 to the power of 18 Newton per coulomb. Please make sure you are checking out our calculation. Alright, very important. So this is what you will have as your electric field. So therefore, we just impute that, right? Now, since we're looking for distance, obviously we can't make use of V because we want to find distance. Now let's do something now. Under this potential energy, watch. So therefore, potential energy will be equals to the electron charge times, these are writing this V now, right? ED. Right, ED, why? Because we can't get V because we're looking for D, right? So instead of writing V, just put ED. Since we have E, and remain D. So that is very simple. So therefore, if you make the distance subject formula, you have that distance is equals to the energy divided by what? Charge times electric field. Alright? Charge times what? Electric field. I remember very well that charge times electric field is force itself, and this is dimensionally correct because energy over force gives you distance, right? So therefore, impute our energy what has 1.6 times 10 to the power of negative what? 17, all divided by what our charge 1.6 times 10 to the power of negative 19. Our electric field is what? 2.26 times 10 to the power of 18. Therefore, the distance between two of them will be equal to 4.42 approximately times 10 to the power of negative 17 meter. I hope I am correct with my calculation, right? So this is our distance. That's easy as that. Please remember that if you have any question, please put them in the comment section. It's very important so I can address that. So this is the answer to this question, alright? So anytime you see the word electron volt, your mind should go into getting energy. And now I'll give you a preview of what we'll discuss in capacitance, which is that energy or potential potential energy is equal to electron charge times what the potential itself, or the voltage, anyhow you want to say it itself. And this is all for this question, right? So let's now move on to another question. So an electron remains stationary in an electric field directly downwards in the Earth's gravitational field. If the electric field is due to charge on two large parallel conducting plates oppositely charged and separated by 2.3 cm, what is the surface density assumed to uniform or be uniform on the plate? Alright, this is very, very simple. So solution, how do you solve this question? Now what is given to us? The first thing, wow, very few variables, alright, or very few constants, and I want to put it. Now it's an electron, so since a particle is being specified electron, you should know that we should expect something like the electron charge, which is 1.6 times 10 to the power negative 19 coulomb, alright? Remains stationary in an electric field directed downwards in the Earth's gravitational field. If the electric field is due to charge on two large parallel conducting plates oppositely charged and separated by, now give us a distance, call it D or R, right? So R is 2.3 centimeter. So you convert this to meter, that gives us 0.023 meters, right? So that's what is the surface density? Surface density or surface charge density are talking about the same thing. So we have to find the surface charge density. Alright? This is pretty simple. Now what is the right formula to use? We have Q, we have R. Let us find density. Now electric field is equal to what? Surface charge density over what? Epsilon naught, right? But we know what electric field is. But we can get that from K, Q, or maybe the Q charge of electron, right? Divided by R squared equals to surface charge density or what? Epsilon naught, right? So now the main thing I need to make was the surface charge density, the subject formula. And how do you do that? So by cross multiplying first. So when cross multiply, you have that surface charge density times R squared is equal to what? K QE epsilon naught. So therefore you divide both sides by R squared to get the surface charge density. So you get that surface charge density is equal to what? K QE and this or what? R squared. As easy as that. So therefore our surface charge density. What is our K? 9 times 10 to the power of 9. What is our QE? 1.6 times 10 to the power of negative was 19. That is charge of electron. Epsilon naught is 8.85 times 10 to the power of negative 12. All divided by our R squared is 0.023 all squared. And if you do the calculation, that will give you something like 2.41 times 10 to the power of negative 17 coulomb per meter squared. Please make sure you're checking all this answer, alright? Because head calculation can differ. So that is the answer for the surface charge density. So you can see this is very, very simple. In our last question, we asked to find the distance also, right? And they gave us potential energy. So you should know what's being given to you and you should know how to apply it very, very well. So these are the kind of questions you see, alright, in your test or exam about surface charge density under electric field. I'm sure by now you've learned it. Any question you have, remember to put it on the comment section. Okay, so please everything about surface charge density under electric field. Please remember to like and subscribe. I'll see you in the next class where we'll talk about the capacitance of a capacitor. Right now, I will say bye for now.